Yeah, so the framing of this is that machine learning models can only take in one very specific kind of data, and that data is a list of numbers. There's no other way for machine learning models to operate, arguably with the exception of decision trees, but even then, it always comes down in some way, shape, or form to a list of numbers, a vector, in other words. So if you have data that looks like a table with a bunch of numbers in it, it's not hard to imagine how you turn that into a list of numbers. Usually every row is a vector, you feed that into a model, and away you go. The problem when it comes to text is that it's not immediately obvious how you could treat text as a list of numbers. How do you go from a word to a list of numbers, a vector like this? So this really is going to be the crux of what word vectorization is all about, what word embeddings are all about, is finding ways to move from word space to vector space that have valuable properties, that generate vectors that are useful in some way. And so along the way, we're going to have to figure out, what do we mean by useful? What does a useful vector look like? And what I want to do is actually introduce one possible strategy that, for different reasons we'll see in a second, is not actually going to be an optimal strategy, but one possible way to solve this problem of going from word space to vector space is to just use what's called a one-hot encoding. And so the way a one-hot encoding works is, you can imagine in the dictionary there's like an index for every word. So the very first word maybe is aardvark because it starts with two A's. So maybe that's word number one, or a word, let's say, in position 0 if we're going to be Pythonic. And then the next word might start with A, B something, abracadabra, and then that's index number 1, and then the next one's index number 2, and so on. And so what we have here is a vector with a 1 in the position that corresponds to the word that we're trying to represent, and zeros everywhere else. And so this is a 1 at position 0, the very first position, and that's going to stand for aardvark. And apparently we have a very kind of short dictionary because the next word is cat. So we put a 1 in position 2 here, and that's going to represent cat, and zeros everywhere else. And so this so-called one-hot encoding structure is pretty common. You might have encountered it already. You probably have in different contexts to embed different kinds of variables and so on. This is one way we could imagine naively embedding our words into a vector space. The problem is, actually, it has quite a few different problems. Does anybody have a guess, or does anybody want to try guessing what some of the problems with this might be?
Well, I could see. Well, first of all, it's if we want to try even catch a simple language model, like let's say just all the words in the English dictionary, it's going to be a giant matrix. Too big to kind of fathom. That's one. Second one is, it doesn't really know the context and what does the word mean. It just knows the word is there, and depends if we're going to do words or characters. But either way, it just doesn't have any sort of idea of what does that even mean. And when you put that into a model, you want that word to carry, or character to carry, some weight depending on what you're trying to do.
Yeah, excellent. So
where the whole embedding idea, I think, came from.
Exactly. So yeah, so you just hit the nail on the head there in two different, I was going to say two different dimensions, but yeah, two different ways. So the first one is exactly that. So like this, the English language has, depending on who you ask, like around 1 million, order of magnitude, 1 million words, something like that, certainly hundreds of thousands. So if you try to do matrix algebra on a vector that has like 500,000, 1 million dimensions, like that's not going to go very well for you. And so these unwieldy vectors are really not the kinds of things we want to be working with when we're building a live system. So that's reason number one. We would love to find a compressed version of this really 1 million dimensional or so vector. And that's because this is really no good. This would have to go on for forever. And the second thing is, yeah, as Nicola said, I mean, aardvark is in position 0, so it's the very first entry in our dictionary. But that doesn't actually tell us anything whatsoever about what an aardvark is. There's nothing in this vector that gives us a hint about the properties of aardvarks relative to cats. It's totally arbitrary. In fact, we could just decide to call aardvarks bardvarks or something, and all of a sudden their position in our vector would completely change, and yet nothing would have changed about the meaning of the word. Another way to see this is synonyms, right? So like running and sprinting can look completely different in this representation, even though they're very similar semantically. And so we would like a way of representing these words that is both compressed and more semantically meaningful. So those are the two desirable properties that we're going to be going after as we try to construct a more clever way to do this. So actually, this is Nicola's first point. So we have hundreds of thousands of words. These vectors are ridiculously long, and you don't want to be doing matrix algebra on, like a 1 million by 1 million. I guess that would be like a trillion parameters. You would need to make something bigger than GPT-3. So okay, here's the game plan. Somehow we want to go from a word dog, or a word like dog, I should say, to some intermediate representation, which is actually going to be kind of crummy. Like we don't want to end up stuck here. But this is actually what we're going to start with. We're going to start by constructing one of these one-hot vectors. And then what we'd like to do is compress that vector from, let's say, like a length of 1 million to a new vector with a more manageable length, like let's say 300. And we'll circle back around to why 300 or 200 and not like 10,000 or something. We can talk about that later. I actually happen to think that it's a fascinating topic to talk about what the optimal lengths of these word vectors should be. But for now, let's just say we want to compress this a whole hell of a lot. We want to go from something like 1 million to something like 300. And in the process of doing that, what we would like is for the vector that comes out the other end to have values, to have entries whose values tell us something about the meaning of that word. So like, maybe this is oversimplifying, but it would be lovely if like the first dimension of this vector told us something about how animal-like the word was, and maybe the next one tells us how electronics-like the word is, and the next one's like how food-like the word is, and so on. So that just by looking at this vector, you can get some idea of the meaning behind the word itself. That would be a great success if we could embody those two properties, so a more compressed, a kind of shorter representation of the vector, so that we can do math on it more easily, and a semantically meaningful representation where each entry gives us some information about the actual meaning of the word. So this is the holy grail. This is where we want to land. And we're now going to look at like the strategies that get us there. It's going to be hopefully a fun ride. So actually, any questions about this so far? Cool. All right, so let's start with a provocative question. How do you turn a big vector into a small vector? How do you turn a high dimensional vector into a low dimensional vector? So this is focusing, by the way, on the first kind of component of what we want, which is to reduce the dimensionality. So if you want to go from a vector that's got 1 million dimensions to a vector that's got 300 dimensions, what kind of object could we hit that vector with that would give us a smaller vector out? What is it that you need to do to a big vector to turn it into a small vector, other than just say like cut off a whole bunch of the dimensions arbitrarily? Is there a mathematical tool that we can use for this? Whoops. Sorry.
PCA?
Okay, PCA, good. That's a really good point. PCA is one special case of the operation that I'm going to describe, but you're absolutely right. The more general answer I was kind of looking for was just use a matrix, right? And PCA,
matrix multiplication, yeah.
Yeah, but you're exactly right, Nicola. Like PCA it's just a matrix. But
it's the idea, yeah, that's it, yeah.
Yeah, that's it. So we've got a long vector. In this case, we're imagining a 6-dimensional vector. I know that in the earlier example, it was like a 1 million dimensional vector. We wanted to get down to 300. Here we're looking at a 6-dimensional vector, and we want to get it down to 2 dimensions. And if you've done linear algebra recently, or you're comfortable with this, hopefully it'll be obvious. If not, just to run through it really quickly, the way these things work is you map this row onto this column. So you go 1 times 1 plus 2 times 0 plus 0 times 0 plus 0 times, and so on. Anyway, the calculations are actually here, and at the end of the day, you get a vector that looks like that, 8 and 4. Okay, so somehow using a matrix, you can actually just like reduce the dimensionality of a vector. So the number of columns in that matrix is going to have to correspond to the number of dimensions in your vector, and then the number of rows in the matrix, that gives you the number of rows in the output vector. And so using a matrix, we can arbitrarily specify how many dimensions we want to map onto how many other dimensions. So this is just clearly going to be the tool we're going to have to use. We're going to somehow have to find a magic matrix that we can use to hit a vector like this one hot encoding of the word dog to produce something that has all the properties that we want. Shorter length, like 300, and these entries that are actually semantically meaningful. So somehow we're going to want to get that out of this matrix. So the only take-home message really so far is somehow a matrix is involved. Somehow we're going to have to figure out a way to come up with a matrix that hits the one hot encoded vector we're going to have to produce something meaningful and more compressed. Any questions about this so far? Cool. All right. Cool. So, right. So here I'm just being explicit about kind of the comparison here. So you can imagine, like, this is the one hot encoding representation of the word dog, because in our imaginary universe, dog is like the first word in the dictionary for some reason. We hit it with a magic matrix, we get a compressed version of the word dog out the other end, and you'll notice that the values now are different from, it's not just a one hot encoding anymore, we now have different values, right, a 1 and a 4. And so ideally, what we would want is for these values to actually be meaningful. We want those values to map onto, like, how maybe the 4 is like, this is its animal score, and the 1 is its like airplane-ness, something like that. And clearly it's like it's dominated by its animal score. So, cool. What should this matrix be? I mean, I've been pumping it up a whole hell of a lot here. This matrix obviously somehow is important, but we're going to have to figure out a way to define its properties, define its entries. How do you figure out what values this matrix should have in order for this compressed version of our word at the end of the day to actually be useful for something? And, well, here's an intuition. Actually, sorry, it's an intuition I've already shared, but I'll just repeat it again. This matrix should just be whatever it needs to be to make this compressed vector useful, to make it semantically meaningful, to make it shorter. So those are the two properties that we want, and we want that matrix to accomplish those things. But now, useful for what? I mean, like, it's not clear mathematically. Like, I've said things like, well, it would be great if each entry in that new vector corresponded to some property of the dog. Like, the first entry tells you how food-like it is, the second entry tells you how animal-like it is, and so on. But, like, how do you express that mathematically? How would you even train a system to have a property like that? And that's what we're going to look at next. So I'm going to throw out a proposal, and that proposal is the following. If I have a representation of a word that is useful, then that representation should be useful for making predictions. Specifically, it should allow me to make predictions about what other words are likely to show up near this word. Okay, so the intuition here is that words that are more semantically similar, words that have similar meanings, will tend to show up closer together in a piece of text. So, for example, dog is pretty similar to cat, so you kind of expect them to show up a lot close together, right? Maybe there are a lot of articles talking about different animals, and so dog and cat and pony and so on, they all kind of show up nearby. And if that's true, if more similar words, if more semantically similar words end up showing up close together in text, then what we should be able to do is use whatever the embedded representation, the compressed representation of our word is, to predict which words should show up nearby. So basically, this should be useful for that prediction task. I should be able to feed this into a model, like a logistic regression, for example, and that logistic regression should be able to spit out the probabilities that every other word in the dictionary will show up close to this word in a window of text. Does that make sense? I can kind of explain that in a different way if it doesn't.
I think it does. The way that maybe it will help folks, like when it clicked for me what embeddings are, it's just imagine representing a word with a bunch of features. It's just if you have a table, and then if that table has 25 columns, and then rows will be words. Like each of those columns will represent a feature, and then that's kind of how, you know, that's how I see embeddings. You know,
Mhm.
it's very basic, but it's essentially what it is, I think, and you know, it might help folks. I don't know.
Yeah, absolutely. And like to tie that into what we were talking about earlier, so this is basically the idea that when we looked at this initially, right, we talked about how somehow we want this representation where every entry corresponds to a different property of the word, right? So the first entry tells us how, I don't know, how animal-like the thing is, the second is how car-like or whatever else. Yeah, so that's the desired output. You're right, Nicola. So we want a vector with entries that are semantically meaningful. The question is, how do we get that? How do we actually, like using a computer, how do we go from the word dog to this one hot encoded vector, then ultimately to this like useful compressed vector? And this
Yeah.
last step is kind of what we're going to explore
Oh,
with
okay.
this.
Sorry, I didn't. Yeah, maybe missed that. Oh, yeah. Then language models. Sorry about that.
Yeah, no worries. So the hope here is going to be to explain like how these language models are actually trained, and in particular, I want to look at one example, which is Word2Vec, the sort of classic language model from 2013, 2012. So here's the intuition. Our word, if our word embedding, in other words, if this compressed vector is actually going to be useful, then it has to be useful to make a prediction. What kind of prediction are we going to want it to be useful for? Well, let's start by just assuming that we're going to try to use it to predict what words are going to show up near that word. Okay, so we feed in the word vector for dog, which now is 1, 4, to some mystery algorithm, and that algorithm has to try to predict what other words are going to show up nearby, using a logistic regression, for example. And the intuition is if we if we have word vectors that are actually good, then that prediction will happen effectively. It'll be able to we'll get good accuracy or good performance. And so let's try to do that. Let's try to predict what words are going to show up near a given word using the embedding for that word, using the compressed representation of that word. So here is the full problem, and we'll go through it step by step. So we start off by saying, okay, I give you a word, I don't know, at the very beginning of the dictionary, like aardvark. Okay, so this is the one hot representation of that word. Let's assume we have a magic matrix that is it's perfect. It does a really good job. It's going to compress our vector down to a compressed representation, to the embedding, and it's going to do that in a way that gives meaning to the entries in that vector, just like what Nicola was talking about. Basically, the first entry, tells you how food-like this word is, and the second entry tells you how animal-like, and the third entry tells you how car-like, and so on and so forth. Somehow this matrix is doing that. Okay, so let's assume we have that. I know this is a tricky assumption to make because I haven't told you yet how we would generate that matrix, but we're going to have to kind of go through the structure first, and then in retrospect, it'll be obvious or clear, hopefully, how that matrix will take shape. So we'll start with this, and then we take this. We now have this perfect compressed representation of this word. We're going to feed it into a logistic regression algorithm, and that algorithm is just going to predict the next word, let's say, in whatever body of text this original word was pulled from. So, for example, if dog was fed in, then maybe, I don't know, maybe the most common word after dog is and, because people like to write the dog and the cat or something like that. And so you would hope that the logistic regression, if the representation of the word dog is useful, if it's right, then the logistic regression will predict that the word and will follow with high probability. And so that would be the ideal way that this whole system would play out, right? You'd have a magic matrix that just does a great job at compressing our one hot vector down so that it's both shorter and more meaningful. And the fact that these entries are meaningful is going to help out that logistic regression because now they're features that the logistic regression can pull at to make these predictions. And so the question now becomes, of course, how do we figure out what this matrix should be? and how do we train that logistic regression? And the answer to both is backpropagation. So you actually are going to set up this matrix. If you're familiar, that is, with backpropagation, if you looked at neural networks, let's say, then hopefully it'll just be clear with that one word how all this would work. If you're not familiar with backpropagation, I'm going to mangle the concept very, very slightly here, or actually somewhat badly, but hopefully to give you the flavor. So the idea essentially is we're going to use a glorified kind of trial and error. We're going to try, like, oh, what if we change this value in the matrix? What if we move it up a little bit? And what if we make this one a little bit smaller, and so on? And so we tweak things a little bit, then we rerun this whole process, and we see how the performance works. If we do poorly, we tweak some other values, we try again, and we do this over billions and billions and billions of words until eventually this matrix is actually tuned. And the logistic regression is as well. So they're kind of trained together. Any questions about that? Oh, great. Yeah, thanks. And actually, sorry, I'm just going to step out. I'm going to grab some water. But does anybody have any questions about the setup so far? Okay. Hopefully it makes some kind of sense. This is really the extent of the challenge here. This is the hardest part of the whole thing. If you're able to get this, then you understand word vectors actually probably better than most people who use them day to day in terms of how, especially word2vec works. Yeah, so what we end up with at the end of the day is, again, it takes a whole lot of training, right? Like a ridiculous amount of training. Typical training corpus, that is the body of text that's used to train these algorithms, is billions of words in length. A common source of text is what's called the Google News corpus. And so this is basically just like all of the Google News articles that have ever come out, or that had come out as of whatever year the corpus was updated. So that's one. Another one is the Wikipedia, I think the Wikipedia Common Corpus, I think it's called. Anyway, so that's, again, billions and billions of words, and pretty much it's all of Wikipedia. So these are the kinds of corpuses that are used to train these massive language models to create essentially just a dictionary, a lookup dictionary, a lookup table with a whole bunch of different words and then their associated compressed representations, just like this, which is the holy grail of this whole exercise. So anyway, just to give you an idea of the scale, you probably don't want to actually do this yourself. Like, as you can imagine, this takes a lot of compute horsepower. And even on a modern computer, like, you don't want to be downloading all of Wikipedia, training your own model for days on end, and then, oh great, now I have my word vectors. So in practice, you can actually download pre-trained word vectors online. And this is actually what I recommend doing. Most people use pre-trained models that they actually, I'll just post a couple of links where you can, actually GenSim is probably the quickest place just to find a pre-trained word2vec model if you're specifically interested in that. But using, PyTorch and TensorFlow, I think TensorFlow, come with their own pre-trained models usually that you can, just like import right away. But if you're looking for something specific, then you can go to GenSim, and they have a word2vec pre-trained model that you can download. And sorry, this whole algorithm, by the way, is called word2vec, as in word to vector. So that's what this whole flow is here. And these things are called word vectors right here, this sort of compressed representation of the word that we're interested in. Yeah, so anyway, you want to go online and find those pre-trained networks, pre-trained word vectors. Don't worry about training them yourself. It's not worth it, and people have optimized the crap out of their setup so that you don't have to. Any questions about that? Cool. Oh, I see some. Okay, yeah. Glad the glorified trial and error thing. I know for those of you who have heard of backprop before, I don't want to make you squirm or whatever, but backprop in its own way is glorified trial and error. I mean, it's like informed trial and error. And Daniel says, with the amount of compute power to train a language model for word embeddings, what are the implications for more complex embeddings? Oh, good question. Do they require the same scale of training? Okay, so Daniel, that is an amazing question. I'm gonna defer it to like just a couple slides later because you're now getting into like I think the really interesting like use cases of this stuff and the questions as to whether you need to train on more than just like predicting the next word, more on like glorified autocomplete, or is glorified autocomplete like I hate to put it this way, but like an AI complete task. In other words, like it, anyway, well, we'll get to it in a minute. I think it's really exciting, especially because of some of the recent results around GPT-3 and stuff. We'll talk about that in a second. For now, though, I just want to highlight one thing which is actually kind of cool. Here I've shown how you can essentially reduce the dimensionality of these one-hot word vectors down to 2 dimensions, right? I mean, that's what we're doing here functionally. And if you can reduce the dimensionality down to 2 dimensions, then you can visualize a word in a 2-dimensional space. So I could have the x-axis be the first entry, the y-axis be the second entry, and this would be the point for the word dog on some 2-dimensional plane. And if I do that with a bunch of different words, I can get a plot that looks like this. And this is basically from I think it's from the original Word2Vec paper. And it shows you how different, how similar words end up clustering close together and different words end up sort of far apart. So you can see here, I'll try to zoom in a little bit, maybe on the right one. So you have, all the countries, first off, are clustered together. So you got Germany, Russia, Spain, Japan, and so on, Turkey. All the cities, likewise, are clustered together. So you got Athens, Berlin, Tokyo, Madrid, and so on. You've got child and woman next to each other. You've got Jesus and Christ next to each other. So these are all words that again, you'd expect to show up very close together, right? And so they're being described as similar by Word2Vec. And that's really an indication that your model makes sense, that it's been trained properly. And that's kind of exciting. Now, there's one more interesting property that you might notice, depending on how kind of excited by linear algebra you are. And that's that the distance from a country to its capital, the vector that gets you from a country to its capital, looks pretty similar, regardless of which country capital pair you're looking at. They're all roughly the same length, and they all point in roughly the same dimension. And that's a pretty powerful hint at one of the coolest properties of these word vectors, and that's additivity. So this is one of the crazier things with word vectors is you can do math with words. You can do math with meaning. So one of the classic examples people give, and this is done to death, so if you're familiar with word embeddings, I'm sorry about pulling the old king minus man plus woman equals queen thing, but you can actually show that the word vector for king minus the word vector for man plus the word vector for woman is actually going to be really close to the word vector for queen. And that's, at least to me, maybe I'm an idiot. Well, I am an idiot, but maybe I'm especially naive. I found this really cool. This is like just a crazy result that you could just do math with words in this way, and it starts to hint at their broader utility. And this, I think, is something that Daniel, or it's related to Daniel's question from a moment ago. Well, I'll get to that in a second. But the bottom line is that if you can capture semantics with word vectors, then all of a sudden, like, all the math that you could do on vectors from before, you can now do it on words. And this particular property of additivity or linearity of these word vectors, actually, if you're mathematically inclined, it comes from the fact that all of the operations that were used to train this model essentially like have linear assumptions about linearity baked into them. That's sort of why this, at the end of the day, it makes mathematical sense that the word vectors you generate through Word2Vec would have this property. But the bottom line is they just have this property. That's actually like crazy handy. And so what you're seeing here is the vector between a city and its corresponding country. This would be something like the vector like country minus city, or city minus country, depending on the directionality. But basically what it's showing you is that vector is sort of conserved. So there's the same meaning. Like if I tell you like we're playing like, I don't know what kind of game this would be, but some sort of party game where I'm going, like Germany minus Berlin. And and the idea I'm trying to communicate to you is like the difference between a country and a city, right? So if I told you like Madrid minus Spain, that's the same thing as Berlin minus Germany. They kind of mean the same thing, whatever that meaning is, and I don't know that I could articulate it. That's what you're seeing with this gray line, these gray arrows that are showing you the kind of arrow from country to city. And so anyway, you're seeing essentially that as a special case of this more general additivity property, which is actually where most of the value for these word vectors comes in, because it's not particularly useful to just be able to plot words. I mean, yeah, it's fine. I mean, okay, I can see that, like, Jesus is close to Christ. Okay, I probably knew that they were similar words already. I knew that Germany and Russia and Spain are kind of similar things. But like, what can I do with this? What kind of interesting data science can I do? And this is where we now get a little bit closer again into answering Daniel's question. Let's imagine that we're working for Amazon, and we have a whole bunch of product reviews. What we can do is actually summarize the meaning behind a product review by averaging together, basically adding together, all the word vectors for all the words in that review. Why would that work? Well, essentially what you're doing is you're making the assumption, and it is an assumption, that the meaning of a sentence is just the sum of the meaning of every word in that sentence. It's not always going to be true. There are words like not or didn't or can't and so on that kind of actually mean that the sentence means the opposite of the sum of its meanings. But for many cases, and in fact, it turns out when it comes to product reviews, for I'll say most cases, it does a pretty good job. So you can actually take a sentence, turn every word in that sentence into a word vector, and then add those word vectors together, and then you get a sense for the overall meaning of that phrase or sentence or paragraph or passage. And so just to show you how that might work, incidentally, one quick thing that you will want to do is get rid of what are called stop words. So these are words that don't actually add any kind of semantic value. They're words like this or was or and or I or am. None of these words really tell us anything about the context of the sentence. So often when you're doing NLP, there are, like, I think from NLTK, for example, and a lot of other libraries, there are libraries of stop words that are like come with the package. And so you can just automatically like drop all these stop words. You can add new stop words if, for whatever reason your use case requires that. So that's one of the steps in natural language processing, in pre-processing and cleaning your data. You want to remove all those stop words. And so you'll go from something like, this umbrella was terrible, it didn't stop the rain at all, and I am disappointed, to, umbrella plus terrible plus stop plus rain plus disappointed. And what you'll do is, in each case, for each of these words, you just turn them into a word vector using the magic algorithm that we just set up here, the word2vec algorithm, and then you add them together. And you get the meaning that summarizes this review. And you can kind of see, like, you're going to catch on to a couple of very important things. Terrible, so obviously, this was bad. Disappointed, it was bad, and it has to do with an umbrella and rain. And just with those pieces of information, like, you can imagine how you'd be able to find, for example, similar reviews or similar products. And that's something that was totally inaccessible to us just half an hour ago when we didn't even know how to turn words into vectors. So a really, really powerful tool. And it, anyway, helps with text analysis. By the way, you can also then plot your text. You could plot product reviews. See, like, which product reviews are clustered together. And this is actually something that you could use, for example, I don't know if you worked at Amazon, you're trying to decide, like, okay, do we have a consistent problem in our system? Like, are people consistently finding that, I don't know, when they go to check out their cart, all of a sudden is empty, or whatever problem? You could use some system like this to very simply kind of map out all the different issues people are having with your app or your tool, and that would allow you to prioritize. Like, oh, it looks like we're getting way more complaints in this category than this one, so maybe we try to solve that problem first. I want to go back to Daniel's really interesting comment from earlier. Sorry. Okay. So, and same as something too. So Oh, great. Okay, same. I'll check that out. Illustrations with additions and subtractions. Awesome. Um, yeah. So Daniel said, right. So with the amount, yeah. So Daniel, correct me if I'm wrong in interpreting this, but there's been a lot of talk, especially lately with GPT-3, about the ridiculous amount of compute that needs to go into training these models. Yeah, right? So in terms of sentence, document summarization, etc., do they require the same scale of training? Um, in general, what seems to be the case is that the problem of natural language understanding, of deriving meaning from text, gets solved by any sufficiently large neural network if all you ask that neural network to do is autocomplete. So this is actually kind of remarkable, and I'm sure this would have been controversial like 4 years ago-ish. But basically, if all you do is this word-to-vec like task of trying to predict what's the next word going to be, what's the next word going to be, and you make a neural network that's large enough, that neural network will eventually, and you train it on enough data over enough time, eventually that neural network will learn everything there is to know about the English language or whatever language it's being trained on. And if you don't believe me, go check out GPT-3. Some spooky, really amazing examples of this sort of thing in action, where just in trying to do autocomplete, GPT-3 ends up learning about connections between all kinds of disparate topics. It ends up being able to solve multiple choice questions. It ends up being able to write entire essays. This is just from being trained on that autocomplete task. And this is why earlier I was saying I think it's possible autocomplete is an AI complete task. In other words, in order to perform optimally at autocomplete, a machine learning model needs a comprehensive model of the entire universe and everything in it. Because ultimately it's trying to predict how different ideas and concepts interact. You know, if I tell you like fill in the blank, in order to fill in that blank with the word blank, I could have probably used a clearer example, but you had to reach into your mind and interact with some really elaborate models of the world where you're going, oh, okay, first off, there's a blank here that I need to fill in because by social convention, we've all agreed that questions phrased in this way require me to fill in a blank. And then second, like, how did you know that the word was blank? Well, you've heard the phrase before, you've heard it in this context. You've heard a lot of other phrases like fill in the blank. You've heard a lot of other sentences that start with fill in the and then have a completely different word there. But just from context, you sort of inferred that, oh, okay, he wants the word blank there. Well, that's not something that's like super obvious unless you have access to that context. And anytime you find yourself using the word context, that's a hint that there's a very sophisticated mental model operating in the back of your mind that you may or may not even be consciously aware of. So, with that having been said, the real complexity is pretty much any kind of task like sentence level embeddings, document level embeddings. They all reduce to this autocomplete task. So if you can solve that, you will solve those tasks as well. That seems to be the lesson of GPT-3. And as we've seen from Word2Vec here, like sentence and paragraph level work can be done by a Word2Vec model that's just trained on that simple autocomplete task. You just have to add together the semantics for all those words, or the meanings for all those words. Does that answer it? Oh yeah, Nicola.
Sorry. Just a quick question. You mentioned that we average across words, or do we just add them up, or do we do averages?
Sorry, yeah. So it is averaging. So the reason,
Okay.
yeah. So the reason is that all. So let me just scroll up here. So all word vectors have to have the same length. They all have to have a length of 1. And this is basically, I mean, it's an important property of these word vectors for different mathematical reasons that we don't have to get into here. But the bottom line is, if all you did was you added together like a whole bunch of words, you would end up with a vector that like could be way longer or way shorter than what you actually wanted.
That makes sense. Yeah.
Yeah,
So you add them up and then you just divide by the number of whatever.
that's
Which
right.
is an average. Okay.
Yeah, you
Cool.
normalize it. So
Yeah.
yeah, exactly. Yeah, Daniel.
Yeah, so with all of these language models, sort of this arms race of language models that we're seeing,
Yeah.
Are these all just better ways of getting a word embedding, or is there something different that's happening sort of at the root?
Yeah, great question. So I'll just flip back to this here. So this is this here is really where we started focusing the conversation exclusively on word2vec. So the particular sequence of take a matrix and then like hit this vector and blah 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 all that. This really is word2vec. What's changed, especially with GPT, is the T stands for transformer, and that's a category of neural network that does something that's mathematically it's similar to what's going on here. It's a bunch of matrix algebra, but in the weeds, it's using something called an attention model that does an awful lot more than what this looks like. So attention models are good at noticing which parts of, for example, an input sentence they ought to be focusing on to extract more meaning. And it's also a much, much larger, much deeper architecture. So there are dozens and dozens of layers of this kind of matrix math going on before we even spit out that first vectorized representation of the word.
And just one more follow-up question. You mentioned that, I guess for a lot of different purposes, you would have the stop words removed, I guess depending upon what your goal is. But with a lot of these big language models, when you see them put to use, a lot of times they're spitting out punctuation and all the stop words. Are they kept in during the training?
Yeah, really good question. So, okay, I'm going to draw an analogy, and we'll see if I can do this successfully. I know the analogy exists, so if this is a failure, it's because I'm not communicating well. If you wanted to use, if you had very little data, you would use a simple model, right? You'd use like a support vector machine, or you'd use a linear regression, or something like that. And the reason that you would have to do that is that there simply isn't enough data to allow a more complicated model to kind of latch on to nuances and intricacies in the data. You need a lot of data to be able to spot sort of subtle patterns. The same is true for language models. So as big as 5 billion words sounds, it's actually not that big. The corpuses that GPT-3, for example, was trained on was significantly bigger. And partly as a result of that, but also just like there's so much more compute power being thrown at the model, so they can afford to make the model more sophisticated, they can afford not to drop stop words. Stop words are kind of like, it's this trick that you use to make your data simpler so that you can get away with using a simpler model so that you don't have to spend as much money on compute. Once you all of a sudden are OpenAI and Microsoft says we're going to give you $1 billion of largely in-kind compute credits, then you say, great, let's make the biggest model we can, let's throw it at the largest amount of data we can, and so on. And at that point, you start to say things like, okay, and let's not worry about the stop words because we actually want it to learn how those stop words add value. So the model is big enough, the amount of data is big enough, and the amount of compute is big enough that together you can actually get away with leaving the stop words. And in fact, the stop words, the punctuation, all that stuff is actually desirable because it does obviously confer some meaning. Yeah. Does that make sense?
Yeah, thank you.
Yeah, no problem.
I also feel like and I don't know if this has been mentioned because my internet has been choppy, but like even like I've been doing a lot of Albert stuff for Jarvis, BERT, and GPT-3. It's all like, sure, it's a very complicated model, but you end up getting the same thing, which is an embedding matrix of the. So it's just a very complicated way of getting an embedding matrix. But I think the fundamentals are right in this picture, which is really nice to see. So I don't know. That's like I just like whenever I get overwhelmed by how complicated Albert is, I just remember that it's just it's just training an embedding model at the end of the day. So it's nothing super complicated.
Yeah, and actually, I think that's a really good thing to point out at this stage to kind of have a step back and say, you know what, like, yeah, BERT, Elmo, GPT-3, Word2Vec, at the end of the day, it's just all these different ways of tying ourselves up in knots to generate a vector that looks like this. Whatever this compression step is, like it could be anything. In our case, we just looked at Word2Vec, but like it's just more and more sophisticated ways of achieving the same outcome. Yeah, I think that's a really good point. And then actually, so one last quick thing. So we talked about you can look at product reviews in this way. Maybe plot them together, notice clusters, and you realize, oh, look at that, people, a bunch of people are complaining about similar things. That's great. But what you can also do now that you have you basically have a list of numbers that corresponds to a piece of text. And we talked earlier about how the challenge with words is that they're not lists of numbers. If we could turn words into lists of numbers, then we could do all the things that we do with lists of numbers, which includes all the machine learning we want to do. We could run classification algorithms, we could run regression algorithms, clustering, and so on. And so I just want to leave with a quick note that this is true, of course, with respect to Word2Vec. So suppose you have a product review that you rip out all the stop words, you end up with umbrella, fantastic, kept, rain, recommend, right? They're recommended. Okay, so you vectorize each word, you add those words together, and then you end up with something like -2 and 0. Now you can take that word, or sorry, that representation of that review, and you can feed it into any model you want. That's why I have a black box here. This could be logistic regression, it could be neural network, it could be k-nearest neighbors, it could be your choice of algorithm, and you can predict, for example, is this review positive, right? Is the sentiment in this review positive? Is it negative, and so on. You can predict, what, how much would a person pay for this product? If you have the purchase price or something, just based on the review, and on and on and on. So basically, you can do any kind of machine learning you could ever want once you have these vectorized representations of pieces of text. It opens up this Pandora's box of stuff that you can do with text data. And then yeah, one last thing actually, just because people, very often people are so excited, surprised, confused by the fact that we can do this, that then they forget about all the non-text data that they have. So for example, let's say I came to you, I was Amazon, and I was like, oh geez, we're really we're I don't know, we're trying to predict how much of each of our products are actually going to sell. And you're like, okay, great, I have product reviews. So for a given product, I can come up with the reviews and then Word2Vecify them and come up with a word vector. But then I also have a bunch of other information, I know what product category it belongs to, and I know the price, and so on. And then this is the kind of word vector representation of the review, this -2, 0, 9, and so on. I just put it in brackets and horizontal just because that way it fits better on the page. But you have a bunch of data other than this word vector, or this kind of combined product review vector. So how do you put that together? Well, the answer is you just glue it together. You append it, and you can create a vector that looks like this. So you have book 20, so property 1, property 2, and then -2, 0, 9, 1, basically just paste in the rest of that vector out here, and now you have a composite vector that has all the features you care about. Really, the bottom line here is that this product review vector, it consists of properties that are useful, and those properties, just like price or just like book, are just new features. And so there's nothing wrong with combining these together, as long as, of course, you maybe want to normalize your product thing. You maybe want to turn book into a categorical variable or something. Doesn't really matter. I mean, you do whatever pre-processing you want to do. The bottom line is you now have what is effectively tabular data. You went from a problem where you had some tabular data, so your product category and price, and then you also had originally this text data, and now you've just converted the text data into effectively tabular data, into a vector that you can now stick to the other vectorized stuff, the book product category and the price, to make a fully vectorized, fully tabular data type, which now you feed into any algorithm. Any questions about that?
Not a question, but I really wish I had this slide 12 months ago, because I was trying to. There's really not a straight cut answer to that question on the internet. Mm-hmm. I barely found a Stack Overflow post that tells I mean, my intuition was telling me this makes complete sense, but no, there was really no straightforward way of doing this. And then TensorFlow, I think, allowed, I forget what it was called, but you can now pass in embedding and other features at the same time. And then like you don't have to. Yeah, so but that didn't exist, I think, when I was looking for it. I can't remember. But it was still frustrating that I ended up not using the embeddings because I couldn't figure out how in the world would I do this. And then it turns out you can just stick them together and
well,
solves the problem, but didn't know that back then.
I'm relieved to hear that, because full disclosure, the reason I added this slide in the first place is that I myself was confused by this, and I was like, to be honest, I was kind of embarrassed to put this slide in because like, oh man, are people going to think that like that I don't get this? And yeah, like I didn't get this. It's not obvious. It's okay to be confused by this. They're different data types, right? Like it kind of seems like you shouldn't be able to just glue them together.
It seems wrong. Yeah, it seems like you should. Like on one side, I was thinking this makes sense, but on the other side, I was like, wait, this maybe doesn't make any sense. And then I just couldn't. And it was some sort of bike review thing. I can't remember. It was like, hey, predict how many bikes we're going to sell or something. And you had a bunch of stuff. And one last thing was the review of the bike. It was I can't remember if it was Kaggle or something. It doesn't matter. But that was a task. And I ended up just using the everything besides the review part. And I got, okay results, but nothing spectacular.
Yeah.
So that was the part I was missing, but I couldn't figure out how to do it. And this is the key slide here. And this actually goes into even if you use BERT or any other very complicated model to your problem. At least that's how I see it. I don't know. That was the bottleneck for me. But
yeah,
I was like, what if I don't want to just do what if I don't want to classify text? What if I want to have this as something else?
Yeah.
Yeah.
No, absolutely. And I think this is one of those traps that people fall into very easily is, they'll say, oh man, now I have to like decide whether I'm going to look at this as like a tabular data problem or a natural language problem. And they're kind of like, they get stuck there and they're like, oh man, anyway. And by the way, actually, just one more thing too, to generalize even further. So you actually, suppose that you had like 2 reviews for each product. You actually could have like another column with review 2, and then you could just stitch like this vector onto that vector onto these other 2 things as well. Like there's no reason that you can't like smush things together even more, other than the fact that the dimensionality at a certain point does get too high and you got to worry about overfitting, which is fair. But so I'll just leave you with this one kind of maybe fun example, hopefully. So way back in the day, when Ed and I were building a restaurant recommendation app, this is like 2015. So what we did was we would look at reviews for restaurants. Oh no, sorry, it was like descriptions of restaurants or something on Yelp, and we would do this. So we used Word2Vec to like construct these word vectors that represented each restaurant. And so we would combine them together. We would have a 300-dimensional vector and a 300-dimensional vector. We'd glue them together. And then we would feed that 600-dimensional vector into a machine learning model that would then try to predict how likely a person who went to both restaurants would be to like those to like the other restaurant. Like basically, you give me a restaurant that you like. Okay, I'll take that word, the embedding, the vectorized representation of that restaurant. And now let's pick a restaurant that I'm wondering about, and we'll feed it in here, combine them together, feed them into a model. The model mixes the features of both restaurants together and then determines a score for how likely, how compatible basically those restaurants are. And anyway, this is just some of the crazy stuff you can start doing with these things. Which is, at least I think, kind of exciting.
That's pretty cool. How did it work out? I'm just curious.
Not
the success of the startup, just that specific problem.
Oh, okay. Yeah. No, great question. I mean, it was marred with overfitting issues, but we did have a pretty big data set. Ultimately, we were able to use some people who like reviewed multiple restaurants as kind of the basis for that. Yeah, and it worked decently. The only problem is nobody wanted it. So lesson learned.
Yeah. One thing that I was going to ask you, and you might, I find that like a problem of summarizing paragraph embeddings maybe is still not super like, hey, you should do this.
Yeah.
Because people are like, oh yeah, you should maybe just, how about you get all the sentences and then you average out across all the sentences, and then that, like that's your document vector. Because I was trying to figure out how would I get a document vectors, and basically the solution was you convert sentences into embeddings and then you take an average, and that's kind of like, here you go. But it seems like it's not, like you're gonna lose some information because you're cutting it out into a dimension.
Yeah, definitely. Yeah, and in fact, this problem of abstraction, right, kind of follows us all the way up the ladder of like text scale. So, like for example, when you're focused on word scale, a word like not, when it's placed in front of another word, completely negates the meaning of that word, and now all of a sudden you should be interpreting it the opposite way. You could imagine at the level of sentences, like I could write a sentence like, the following sentence is a lie, and then the sentence after. And the problem with like sentence level summaries is that you wouldn't catch on to that relationship between those two sentences. Now, just like earlier, you wouldn't catch on to the relationship between two words like not and then something that follows. So yeah, this is always a problem, and the hope is that as you scale up more and more, and GPT-3, for example, is much better at doing this sort of thing, that you're going to get more and more coherent summaries. Yeah.
Oh, okay. So essentially it's saying, hey, if you have large enough thing to average over, it's still going to catch those nuances.
Yeah.
Okay, that makes sense. Oh, yeah, I was hoping that there's, I just, whatever I looked, Hugging Face, whatever, they're all like, yeah, just average it over, it'll be fine. I was like, I don't know. Yeah, it seems fine, but it's not, but that's good to hear. Yeah, that makes sense. Yeah, thank you.
So I'll make one last point here, and I don't want to, like, please feel free to hop off, folks, if this is not interesting. But I do want to make one last point that I think is really important, and it points to exactly, Nicola, what you just raised. So I always talk about how taking the average, the mean, is actually a machine learning algorithm. Like, not a lot of people think of it that way, but it actually is. It's a dead simple, really stupid machine learning algorithm. The more samples you get, the better the average gets at representing whatever thing you're trying to predict is. So it has all the properties of a machine learning model, except it's a really dumb one. And what's happening when we're doing this word vector averaging is we're secretly, it always takes a model to get you from a collection of inputs, like a collection of words, to a summary of the meaning of that collection of things. So, for example, it takes a model for you to go from a list of word vectors to a summary vector for a sentence, right? If I have a sentence with a bunch of different words and I want to combine those words together in some way to give an overall meaning, there's some model that I need to apply to go from level 1 to level 2. That model, in the example we've been looking at today, is averaging. We just say, whatever, we'll like average the vectors together. Well, that's a machine learning model. It's a very naive model. And Nicola, what you just pointed out is like, yeah, some people take it one level further. They say, actually, you know what? I'm not going to do that. I'm going to actually like learn at the sentence level, but then I'm going to average sentences together. So again, there's always that little extra step where when you want to aggregate all that information together, you are going to end up applying some model, and that model can be sophisticated, like GPT-3, or it can be naive, like Word2Vec, or like a lot of the Hugging Face models where they just say, you know what, we'll just average together the sentences. So I think thinking in terms of like noticing where we're secretly applying these models is worthwhile in some cases.
That's actually, I never thought of that way. That makes a lot of sense. It's almost like that dimensionality reduction.
Yeah.
Without really, it's very stupid dimensionality, but it works. Yeah, that's interesting.
That's right. Actually, I mean, really, like any situation where you're taking a large number of inputs and you're producing one output, and that includes averaging, that is dimensionality reduction, right? You're taking in a large list of numbers and you're like getting one number out at the end. It's just that, yeah.
I wonder what would happen if you put an actual neural network in between. Like if you have a bunch of paragraph embeddings, and then you kind of plug those through a neural network, what would be spit out in the end?
Like if you replace the average with like more layers of neural network.
Just a neural net. And I honestly, like, I I did attention a year and a half ago, not self-attention, and if you know sequence models, it makes sense. But then self-attention, I read I tried to read the paper, the parts that I'm interested in, and anyways, that's I'm going besides the point. But it will be real interesting to see how a pair. I passed at a bunch of word embeddings, and I want to get a document summary at the end, just with a neural network, like what would happen. And I bet these things exist, but it's just something that came up in my mind.
Well, yeah. So to give you an idea, like GPT-3, it's what's called its context window, basically the part of the text that it's aware of
Yeah,
during training. Yeah, it's over 2,000
that makes
tokens,
sense.
right? So yeah.
Oh
So
wow, 2000
yeah,
on GPT-3. Whew.
yeah. So
Yeah.
so this is part of what makes GPT-3 so powerful. One of the problems with Word2Vec is I think the window is something like 4 or 5 words during training, right? So you can kind of see that difference in scale playing in there, and that's part of that's the context, right? That the algorithm is able to keep in RAM at a given time, and this is where GPT-3. There's an argument to be made that that context window already makes it potentially superhuman in some ways, because if I'm reading like a 2,000 word article, like I can't remember word number 1 when I'm at word 2,000. That's all escaped from RAM. So anyway, that's not quite a fair one-to-one comparison, but sorry, one last really quick thing. I just forgot that this big mystery that I planted at the beginning, I never tied up this loose end. The length, 300 dimensions. You might be wondering, why is Word2Vec, or why are word vectors generally 200 to 300 dimensions in length? And really quickly, the answer is that's the dimension that makes them best at making the kinds of next word predictions that they're trained on. So when you try messing around with like the length of this compressed vector, it turns out that 200 to 300 dimensions ends up usually doing the best job. And why is that the case? Well, it definitely implies that every word in the English language has usually around 200 to 300 dimensions worth of meaning. Because what this is saying is like, hey, if you want to turn these words into vectors in a way that makes them useful for predictions, then use a 200 to 300 dimensional vector. And that means that there must be 200 to 300 dimensions of meaning to a given word, like on average or something like that, which I think is kind of an interesting fact about the English language. And in fact, if you generate word embeddings for different languages, you will get a different optimal length, a different optimal dimensionality for that compressed representation. So anyway, just a little kind of cool tidbit I thought.
That's awesome. As one thing that I started, you can't see my camera turned off, but Jeremie Howard, the guy that runs Fast AI, he's like, why do we pick this number? Well, we tried a bunch of things. Turns out this one works the best, and then they derive meaning afterwards, after they pick the best number. So I feel like that's the same thing here. It's like, oh yeah, we tried a bunch. This one works best, and then we thought about it, and then there you go. So it's kind of funny how a lot of these complicated math things actually came from trying a bunch of things and then deriving intuition from backwards. But
yeah, that's almost like the definition of machine learning in a way. It's like
yeah.
Let's outsource the thinking to a machine, and then at the end we'll be like, oh yeah, these observations totally make sense because reasons. Yeah. So.
Yeah, because we're smart. Yeah, and then we can. Yeah, cool. All right. Thank you, Jeremy. This was really good. I love that.
Great. Well, I'm glad. Yeah, and folks, feel free as always to ping me on Slack or wherever else with questions if you want to follow up too. So, I think I'll leave that there and have a great day, everyone.